Hi, today we will see the Hamming distance problem and we will solve this using Python. The problem statement is the Hamming distance between two integers is the number of positions at which the corresponding bits are different. A given two integers x and y, return the Hamming distance between them. Now here we will see the examples. If the input is x is equivalent to 1, y is equivalent to 4, we have to return 2. And if the input is x is equivalent to 3 and y is equivalent to 1, we have to return 1. So in the first example, x is equivalent to 1 and y is equivalent to 4. The 1, if you see the binary format for 1 and 4, which is 0001 and 4 is equivalent to 0100. In the binary format, the LSB bit, if you examine, the x and y are different. So this bit position we can consider as the variation in the bits. Whereas in B1 position, the value of x is equivalent to 0 in B1 position. For y, the bit is equivalent to 0. As these two bits are same, so this we are not going to be considered the Hamming distance. So the Hamming distance here we can take it as 0. Next we will see the bit position which is B2. In the B2 position, the x and y bits are 0 and 1 as these two are of different bits. So here also we have to consider the Hamming distance as 1, LSB also 1. Now we will examine the MSB bit. For x and y, the MSB bit are having the same bit value. So the here Hamming distance is equivalent to 0. Now if we add all these elements, the Hamming distance is given as 0 plus 1 plus 0 plus 1, which is equivalent to 2. So that we are going to be written as output. Now we'll see the second example where the input x is equivalent to 3 and y is equivalent to 1. So first we will write the binary equivalent of 3 and 1. So 3 we can write as binary equivalent to 1, 1. This is for x value. And y is equivalent to 1. For y is equivalent to 1, the binary format is 0 and 1. Now if you observe the bit format, in B0 position, the B0 bit of x and the B0 bit of y, as these two are of same, so the Hamming distance is equivalent to 0. Next, in the B1 bit position, the x bit, the B1 bit of x is equivalent to 1 and y is equivalent to 0. As these two are of a different bit pattern, here we are going to consider the Hamming distance is equivalent to 1. Now, if we add all these Hamming distances, so the total Hamming distance is equivalent to 1 plus 0, which is equivalent to 1. So now, if you observe these two cases, let us consider one more example. I'll take x is equivalent to 10 and y is equivalent to 7. So 10, the binary equivalent is 1, 0, 1, 0. 7, the binary equivalent is 1, 1, 1. For representing in 4 bits, we'll place MSB is equivalent to 1. So our objective is we had to check the corresponding bit in the ith location of x and the bi bit of y are different. This, if you are able to identify, then how many bits are varying in a particular bit position, that is I, so that we can count and return as Hamming distance. So first, for finding out this case, our objective is x and y. If these two are of same bit, I don't want to consider this case. So this I'll count. Whenever x is equivalent to 0 and y is equivalent to 1, here I want to find out for finding out the Hamming distance that will take as 1. If x is equivalent to 1, in the y bit, vi bit is equivalent to 0, as these two bits are different, here also I want to return as 1 as Hamming distance. If both the bits are 1 for x and y in a particular position bi, So here the Hamming distance is equivalent to 0. Now if you observe carefully, this trade table is analogous to the XOR gate, that is XOR logic. So first step we will take read X, then Y, then we will perform the XOR between X and Y. So whatever the result which is obtained for X and Y, we go for finding out the number of ones in your data. So the number of ones in X XOR with Y. So for finding out the number of ones in any data, so we go for ANDing with 1, then we have to check LSB correspondingly. This is method 1. The second method is, if I take this one as a result variable, we go for ANDing the result variable and the result minus 1. So we are going to AND these two values. One is the result ANDed with the result minus 1. So this logic will clear the first occurrence of 1 from MSB. So we will start from LSB, then we will extend till MSB bit position the first occurrence of 1. Whenever the first occurrence of 1 is we will get, so there we are going to be right, the Hamming distance will be incremented by 1. This is the logic we are going to have. So the various steps we are going to perform is, first we will take one variable, let us consider RES variable. Into this RES variable, we will do the XOR operation between X and Y, and we will initialize the Hamming distance is equivalent to 0. Then we are going to examine till until, so until the result variable is greater than 0, we will perform or we will update RES variable with RES ending with RES minus 1. For each and every step, we go for incrementing the Hamming distance by 1. So the Hamming distance will be incremented by 1. So once RES is equivalent to 0, so then we are going to return the Hamming distance value. Now we will see with respect to one example. Let us consider X is equivalent to 10. The binary equivalent is 1010. Y is equivalent to, we will take as 7. 7 binary equivalent is 0111. First, we will take the RES variable, where RES variable is X XORed with Y. So 0 XORed with 1, 1, 1 XORed with 1, 0, 0 XORed with 1, 1, 1 XORed with 0, 1. So here the result is equivalent to 1101, so which is equivalent to the decimal number 30. So first we'll have the result variable is equivalent to 13. In the binary, we can have this one as 1101. So we will initialize the Hamming distance is equivalent to 0. Here we are checking whether the result variable is greater than 0. So our result variable is 13. As 13 is equivalent to 0, we go for into the while loop. So here we will write the while loop. While 13 is greater than 0, we go for updating RES. So RES is updated with RES and with RES minus 1. That is 13 and with 13 minus 1. Here I am taking this. So 13, the binary equivalent is 1, 1, 0, 1. We are going to AND with 13 minus 1. 13 minus 1 is 12. So 12 binary equivalent is 1, 1, 0, 0. Now do the AND operation. When we perform the AND operation, 1 AND with 0, 0, 0 AND with 0, 0, 1 AND with 1, 1, 1 AND with 1, 1. So here the binary value we are going to get as 1100, which is equivalent to the decimal number 1. So after performing 13 ANDed with 13 minus 1, so the result is equivalent to 1. Then we are going to update the HD value. So now the HD value is equivalent to HD plus 1. So that is 0 plus 1. Now it is going to be 1. Now we go for next iteration. In the next iteration, this RES variable is 12. As 12 is greater than 0, again we are going to be perform 12 and with 12 minus 1. So this will take as RES and with RES minus 1. That is 12 minus 1. So 12 and with 12 minus 1. 12 binary equivalent is 1100. 12 minus 1, which is 11. 11 binary equivalent is 1010. 1011. 11 binary equivalent is 1011. Now we will perform AND operation. 0 and with 1, 0. 0 and with 1, 0. 1 and with 0, 0. 1 and with 1, 1. So now the result binary value is equivalent to 1000, which is decimal equivalent to 8. So when we perform 12 and with 12 minus 1, the result will be updated with 8. As this step is done, we go for incrementing the HD value. Now we'll get HD value is equivalent to 1. So in the next third iteration, the result variable is 8. So now we will write 8 is greater than 0. As this condition is true, then we are going to update RES with RES and with RES minus 1. So the current RES is 8. That will be ANDed with 8 minus 1. 8 binary equivalent is 1000. 7 binary equivalent is 0111. Now we'll perform the AND operation bit by bit. 0 and with 1, 0. 0 and with 1, 0. 0 and with 1, 0. 1 and with 0, 0. This is the decimal equivalent 0. So here RES value will become 0 and HD value will be updated with 1. So now we'll get this one as HD value is equivalent to 0. In the next iteration, as RES is equivalent to 0, 0 is greater than 0 is not valid. So then we go for return HD value. So now what is the value of HD? 3. So we are going to get the output is equivalent to 3. Now if you observe the XORing between 13, when we got this 13 by XORing X and Y, where X we are considered as 10, that is 1010, and Y is equivalent to 7, that is 0111. If you observe the bit format, here we have a variation. Here it is same number. It is we are having a different number. Here also we are having a different number. So in 3-bit positions, we are having a different bit binary format for a corresponding position of bit I. So we are going to return 3 values here. Now we will see the programming for this. We have a function. It is given as Hamming distance, and it is given with a two input x and y, where x is integer type, y is integer type, and we are returning the integer type. So the first step is we are going to XOR x and y, that will assign or will assign to RES variable. So you'll write RES is equivalent to x XORed with y. Next, we will initialize the Hamming distance, that I'll take as HD. The Hamming distance is equivalent to 0. Then we will check while the result we will check whether this RES is greater than 0. So while RES is greater than 0, then we will update RES with RES and with RES minus 1. For each and every step, the Hamming distance will be updated with 1. That is, we will add with 1. So once your loop is done, so we are going to return the Hamming distance. Now in this case, it is present in HD. So we go for return HD. Thank you. The Hamming distance program, the solution using Python.